So it can also be shown that by taking the fourth derivative of our moment generating function, we obtain this, and setting t equal to 0, we get our MGF at 0 is, or fourth derivative of MGF at 0 is going to be 3, which is also equal to our kurtosis. So next. Now, in the next part, we want to figure out the value of a that minimizes the mean squared error, given that our kurtosis is 3. So we will begin by differentiating our mean squared error with respect to a, and we get this. Next, we set our derivative equal to 0, and we rearrange our derivative in terms of a to figure out our value of a, and we obtain twice sigma to the fourth divided by 2 times the variance of s squared plus 2 sigma to the fourth. Next, we want to figure out our variance given that our kurtosis is 3 by substituting in 3 into our variance formula, which we proved in our second part. And we obtain 2 on n minus 1 sigma to the fourth. Now, substituting this back into a, this implies that a will equal n minus 1 on n plus 1, which also implies that a s squared equals n minus 1 on n plus 1 s squared. Next question. Now, if normality is not assumed, show that the mean squared error of a s squared is minimized at that. Also, this is useless as it depends on parameter. So it's basically the same process. We figure out the value of a that minimizes the mean squared error by differentiating it, and we end up with this. So this is our value of a that minimizes the mean squared error while differentiating. Now kappa, or our kurtosis, is just going to be k because we're not assuming normality. So basically we're just rearranging that formula into our form, and we end up with this. So if you want to have a look in detail what I've done, feel free to go through my slide, pause it, have a look, see for yourself. It should be correct. Next part says, show that for distributions with kappa greater than 3, the optimal a satisfies a less than n minus 1 on n plus 1. And for distribution with kappa, kurtosis less than 3, the optimal a satisfies n minus 1 over n plus 1 less than a less than 1. So let's have a look at the solution. So consider kurtosis greater than 3. So basically we're just going to substitute our kurtosis into the formula for a, and obviously if our kurtosis is greater than 3, then if it was 3, if it's bigger, if our denominator is greater than, if we're putting something into our denominator and it's making it larger, then it's going to get smaller. So a is less than what we have over there. Therefore, a is less than n minus 1 on n plus 1. Now consider kappa less than 3. This implies that the reverse, obviously, because if kappa is less than 3, then what happens is our denominator gets smaller. So a becomes greater than n minus 1 on n plus 1. But now we have to figure out what our upper bound for a is if kappa is less than 3. So we know that a is maximized when the variance of s squared will equal 0, which implies that a equals 1. And when a equals 1, our kurtosis is equal to n minus 3 on n minus 1, which is less than 3. As well. So this means that a has to sit in between 1 and n minus 1 plus 1, because a is maximized at that other point. So then we're done. Alright, so that's the end of my presentation. Thank you for listening, and please tune in to any future presentations that I make. Thank you.